In the last video, we met the value e, and we saw that plotting the graph of e to the x, e was that special number where the gradient was always exactly the same as the value of the function at that point. We've got our graph e, y equals e of x still there. We're now just going to meet the log base e. We generally call that ln, some people just call it log or line or something like that. I refer to it as ln, so if I ever say ln, all I'm referring to is log base e. So if I plot the graph of y equals ln of x, we see that it has the classic log graph shape, and if we put in y equals x, we can see that the log graph is a reflection of the exponential graph because it's an inverse. All inverses are reflections in the line y equals x. So let's just have a look at a few properties of these graphs. First of all, we'll just focus on e of x, and we'll think about its domain and range. The domain of this function means what values of x can I plug in to the function. As you can see, I can always do e to the power of a very negative number. I just get a very tiny number out. So if you think of e as about 2.5, 2.7, 1 over 2.7 to the power of 8 is going to be very, very close to 0. Similarly, there's no upper limit on this. I can plug in as high a value as I want. However, by the time I start plugging in numbers like 10, I get extremely high values. So you can see that if I pull the graph down a lot here, always has that same exponential shape, but by the time I get to 2.7-ish to the power of 10, I'm up over 20,000. These things grow really, really quickly. Exponential growth is almost a byword for very quick growth. Okay, so we've seen the domain is any value of x. I can plug anything into it. What about its range? Well, we've already seen that we get very, very high values very, very quick, and it can go all the way up as high as we want. So we'd say that it's unbounded above, or you could say it has an infinite range upwards. As we start plugging in negatives, however, we see that we have over here. We cannot get values lower than 0. And in fact, we can never quite get the value 0. If I zoomed in here enough, eventually you would see there's a small gap between y equals 0 and the value of our graph. However, it takes a very, very long time to zoom in at such high numbers. So let's just zoom in over here somewhere, just see that there is a gap even when it appears there isn't. So e to the power of -6, zooming in on there, we can start to see some daylight appearing. So we'll never quite touch 0, but we can get as close to it as we want. So what we would say is, we would say that the range of e to the x is anything greater than 0. Okay? So we would say g of x is greater than 0. We can go as high as we want, but we cannot quite get 0 because there's an asymptote there, and we certainly can't get anything less than 0. What about its inverse function? Well, because it's a reflection in the line y equals x, we simply see that now my domain is anything bigger than 0. Our asymptote is now at x equals 0 rather than y equals 0. So our domain will be anything bigger than 0. I can plug in any number I wish, as high as I want, but I can never plug in 0 or anything lower than 0. And we also see now that our range is anything. If I change the colour of this so that we can actually see that it's overlapping on that axis, so if I make it red, we can see that the computer's struggling to plot it because the numbers are so small. I can, in theory, go to very, very low numbers. The computer's struggling a little bit though because those numbers are so small. And also, I can eventually get as high as I want. It's just that this graph grows really, really slowly. So there is no limit above. It just takes a very, very long time to reach a great height. So you can see by the time we're at 300,000 on the y-axis, we're only just above 12 on the x-axis, we're only just above 12 on the y-axis. We can get as high as we want, it just takes a very long time to get there. So we've now met the number e and we consider the function e to the x. That's kind of our standard exponential model. You'll see more of why we do that as we study A2 maths. And we also have the inverse of that, ln x. That's just a logarithm base e. So we could have also written that as y equals log, and then we just need to type in the base of x. And we'll see that that gives us exactly the same graph as we had before. So remember, ln of x is just log base e of x, and it's the inverse function of e to the x. All of our log rules that we've met in previous lessons work exactly the same. It's just a special log base that you'll see in the second year is very, very useful when you start solving differential equations and stuff like that. Thank you.